I'm a third-year PhD student in statistics, working pretty much on relational learning in deep multi-agent reinforcement learning. So there are three things that basically come together: relational learning, deep learning, and multi-agent reinforcement learning. And I will try to give you a good overview of all of these things in context of what my work at least. Basically just a little introduction, some preliminaries to help understand the actual method that we're using, some results, and then if we do have time, an outlook on what comes next, okay? So a little introduction, and I think it's probably starting with the multi-agent problem, okay? So just to kind of embed the context a bit, we work in multi-agent reinforcement learning, which basically means we have multiple agents working in a system, okay? I would really love to tell you I'm working on real-world application, I'm saving the world with search and rescue missions, but this is what I'm working on, okay? So it's game simulations, basically. At some point in life, maybe, you know, we'll get there. But yeah, I get to the point later why that is quite hard, just because multi-agent reinforcement learning is fairly complex at the moment. So what we're basically having is we have multiple agents that need to coordinate in a system. They could be collaborative or competitive or mixed collaborative competitive. But what's important for us is that they have some elevated level of spatial complexity or relational complexity, okay? That is a case where you have multiple agents, even strongly more than in a single agent case, because you need to coordinate with multiple agents, but you also need to understand basically the positioning of all of the objects, okay? So because multi-agent reinforcement learning is quite a complex problem itself already, we want to kind of like focus on when we have relational complexity, okay, how can we work with that, okay? Additionally, we also have sparse rewards, and I'll talk about that probably next. Just to formalize this a bit, because I think we need that for the next 20 minutes. So what we have here is partially observable Markov games. And whoever has single agent reinforcement learning, like knows a bit of that, they will find a lot of similarities to what is on here. To give you an example, I basically have a collaborative pick and place environment here, okay? So you have an environment where you basically you have two agents, and one agent can pick up a parcel and need to pass it to the next agent, and then the second agent, the dropper agent, needs to then drop it off at this goal destination here, okay? This is actually quite like spatially complex because you actually need to understand where everything is. You need to be coordinating because you need to pass it to the agent only if it's actually adjacent to you, and then you need to drop it off at a certain destination, okay? So that's the setup here, okay? In this case, we have two agents. We have individual action spaces. You could have the same action space, but in this case, basically what they do is you can go left, right, in all directions. You can pass a parcel, you can pick up a parcel, and you can drop off a parcel, okay? That's basically the action space you have. Then you have individual rewards, and here we have sparse rewards, which basically means that you don't get rewarded unless you actually do something that is good, okay? So you only get rewarded if you pick up a box, if you pass the box, and if you drop off the box, okay? Often you would have dense rewards, which basically means that you're guided to the right direction by having a distance-based reward to the goal you need to go to, okay? Which makes it much easier because you learn at every step what you're doing is right or wrong, okay? But that's what we have in this case, okay? Each of these agents have a policy. That means that they basically take an observation, OI. So an observation here is sometimes the same as the state space, but sometimes also just maybe a partial observation, which means a grid around your agent or not, okay? And in this case, you have an observation and a policy that you act on, okay, on that observation. So you basically take an action in that case. And then in transition dynamics, which takes the state space and all of the actions of the agents and then transforms the state, okay? So for example, if you drop off the box at the right location, you actually get, you're done, basically. And then you have a discount factor, which is basically just important for the optimization problem you have because you want to actually kind of like discount future rewards in that way. Similar to the single agent case, the goal is basically that you have a cumulative reward, so your reward over all of the steps you take, and you want to maximize that, each agent individually in our case, okay? You could have a shared global reward, but that's what we are working with, okay? The only difference to a single agent case in this case would be that now you have actually the reward depends on all of the actions of all the agents, because in this case, when you, for example, need to pass the parcel, you both need to be passing the parcel in order to receive the reward, okay, actually to do the transaction. So here now we have a reward that is individual, but depends on other agents. And also the state transition, ST, now depends on other agents as well, okay? Which means you have now a non-stationarity in a sense, because now if you were to predict the state representation from your perspective, you have other influences, being the other agents acting on that environment as well, okay? So you have a non-stationary environment. Does that make sense so far? And now just going back really quickly, because I realized I forgot to actually talk about the other examples that I have. So these are the same ways, okay? They're structured in the same way, where we now have level-based foraging, where you do the same thing. You have a number of agents and you need to collect fruits. So you need to match the level of your agent. So in this case, you would have an agent of 1, and you need to match the level of the fruit to be able to collect it. So you have sometimes this agent, for example, could be picking them up individually, but other agents need to rely on other agents, okay? So that's why it's mixed, collaborative, competitive. You need to coordinate with other agents in order to get them. And in this case, it's a predator-prey environment where you need to build a formation as a predator to actually pick up the prey, okay? So that's kind of the setup. There are multiple examples, but these are kind of some of the ones we're working with. Okay, that's it. As I mentioned, multi-agent reinforcement learning is not that easy, and it is not easy for many examples, for many reasons. One of them is the sample efficiency. So in multi-agent reinforcement learning, we have a lot of problems when it comes to computational intensity, okay? First off, we have multiple agents now that we need to train, okay? That is an example. Then we actually have many more dimensions that come in, because usually when you learn, you want to incorporate all of the information you have. So if you have information from other agents, you want to incorporate that. The issue comes with, you have 3 agents, that's quite a lot, because for each agent you have an observation and you have the action that you want to learn from. If you then have, 10 agents, that scales really quickly, and that is quite problematic, okay? Then, because of the sparse rewards, when you're coordinating in all these things, you don't really get a lot of information, okay? So you need a lot of samples to actually get to the transitions where you actually get to learn the right behavior, right? Because if you're coordinating and one passes but the other one doesn't, you don't get anything, okay? So it's a lot, like you need a lot of samples in order to actually learn from something here. Okay, and that's why we're kind of trying to tackle the sample efficiency here, okay? And the assumption or the hypothesis that we've kind of worked with is, if we're looking at these 3 examples of this collaborative pick and place that I've showed you, in a way, so like in a lot of standard multi-agent reinforcement learning algorithms or reinforcement learning, these would be distinct states, okay? Because the position is different and stuff like that, they're slightly removed. What we're basically saying, they're very equivalent in the game dynamics that you have, right? Because at the end, okay, sure, this agent here is now sitting there instead of there, but at the end, in order to actually pick up the parcel, still needs to go down and left, okay? Same with this, the dynamics or the optimal behavior is actually the same to all of them, okay? So we want to actually treat them as equivalent, okay? We don't want to make a differentiation. And the reason for that is that the relative position between these are the same, okay? That's what we basically want to use. We want to assume that the relative position is the most important thing, and we want to abstract to this more simple representation, okay, where we forget about the absolute positions, because we don't care about that. We don't care about these being here or here, okay? What we really care about is what we need to do if we want to go left, right, if we want to pick up a parcel or something like that, okay? So that's the first kind of hypothesis we're taking, an assumption we have in here, okay? The second problem we want to tackle is the generalization capabilities. So this is a single agent problem just as much, but even more in multi-agent reinforcement learning, for the reason that we have multiple agents and sometimes you have systems where the number of agents is actually not fixed, okay? So generalization capabilities means, in general, that I have one environment and then I change something, okay? So I change the number of agents and I change the number of fruits in this case, okay? And this is a really hard problem because of the invariances, okay? As soon as you change something in your from your training data, everything breaks down, okay? But the idea is basically, if I was to learn, okay, how to sit down on this chair, I would learn it, I'm Yeah, imagine I'm not capable. I would learn how to sit down on this chair. In an ideal world, I'll be able to, if I've learned that, to be able to sit down on this chair just as much, because the task of sitting on the chair is exactly the same, right? The problem with these kind of things is that as soon as you change something, which is in this case the position, these kind of models fail really easily, okay? And that's a very naive example, but it happens quite a lot, okay? So we want to be robust towards these changes that actually don't make a difference to the task itself, okay? And that's where the relational representation comes from, okay? So a relational learning representation is just much more robust to that, and we are able to represent these things as equivalent here, okay? And you're also able to actually change something as, for example, the number of agents or the number of fruits, okay? And so that's kind of the thing we want to tackle. And a lot of, as I said, a lot of deep learning methods actually don't cater for that, because you feed in a fixed vector, fixed length, okay? And you basically have no structure at all in this, okay? But we want to impose this structure in our learning scheme, okay? We want to impose that the spatial relations here actually matter, okay? And you want to learn over these rather than anything else. So what we really want to do is use deep learning methods that have more structure in them, okay? Famous one is a convolutional neural network, which has a local structure, right? Where you basically aggregate everything that is around you, okay? But what we are using is a graph neural network, which is even a much more flexible structure, okay? Where you can basically impose any structure you want, but that's the idea. So that's the two things we want to tackle, okay? And with that in mind, I would talk about my method. And I'm just going to chuck it all on there and explain it step by step. But just to kind of summarize again. So our goal is that we formulate an abstraction, so a mapping, a simplified mapping of the observation that we receive that leverages the inherent structure, so the spatial structure, which is always there, right? We're not making any assumptions. We always have the absolute positions. So the inherent structure of the spatiality is always there. So we want to leverage that in order to learn over that, okay? And we want to learn over the invariances. With invariances, I mean the shift that we have here, okay? When I'm here, shift, so the translation shift, for example, that's the things we want to learn over. So that's the goal, okay? And the way we want to do it is that we take an observation and we want to induce structure, okay? And as I said, because graph neural networks are so flexible in inducing structure, we want to represent this grid as a graph, okay? And that's basically the first step. First thing I want to do if I want to have a graph is I want to have entities, right? And that's a really easy step here, okay? Because that's what we already have, okay? We can have a question of if all of the cells should be entities, like empty entities, or if only the objects wanted to be entities. But to be efficient, we're just picking the agents and all of the objects in the environment, okay? So we're taking these objects, and usually they have some features, like, for example, in this level-based foraging, they have a level that they have. But yeah, whatever is available in the observation, okay? It's just a feature of the node, okay? So we're treating them as objects rather than as some grid entity. With that said, we have our objects. And the second thing we would need is the relations, okay? As I said, the relations here we want to induce are the spatial relations, because we don't need to do any hand engineering to introduce these relations. They're always there, okay? So in order to do that, we use a really simple method, which is we say deterministically, okay? If my relations, or so if I'm the agent here, all entities and objects that are on this side are right of me, right? That's all I'm doing here, okay? And I'm doing that for all different directions. I'm doing that for bottom and for top and left as well, okay? That's the same. Then we're adding another relation, which is just that if something's aligned, okay, which is just helping us get a spatial understanding. And if something is adjacent, okay? And if I have these 6 relations, the idea is basically that I'm pretty good in approximating spatial awareness, right? Because if at the end of the day, if an entity was here, I don't know the absolute position, but I know it's exactly where it is because I know it's bottom and it's right and it's adjacent of me. So it's enough to know that it's just these 3 relations, right? The same way as if an entity was here, yes, I don't know exactly where it is, how far it is, but I know the important things that I need to go right and down in order to reach it, you know? So basically what I'm doing is I'm reducing it down to these relative relations in order to simplify my state, okay? And this is just deterministic. I'm just deterministically defining those edges, okay? And they're directed edges. So if something is adjacent, then I connect that in my graph, okay? And that's how I create that graph, okay? This graph, just really quickly, does change at every step, right? Because my objects move along, okay? But that's okay. That doesn't constrain us. With that in mind, that's really good news because now we have a representation of the observation that is very structured, right? We have everything that we know now, and if we know now is spatially relationally biased in this case, okay? And this is really good because now we can actually learn over that, okay? And that's where the graph neural network comes in. So really quickly, a graph neural network for anyone who has not seen this before. So imagine we have a graph, just a binary graph in this case. And what a graph neural network does is it aggregates all of the information from your neighboring entities, because the assumption is basically like, in order to inform your own representation, you want to take your neighbors. Your neighbor says a lot about your own representation, okay? So you aggregate the information about your neighborhood and update your own node representation, okay? That's basically how it works. So the aggregation could be anything. It could be a linear transformation, you know, and then you sum over them and average them, and then you just update your own representation with some nonlinear function, okay? That's the normal graph convolutional neural network. In our case, because we have 6 relations, we have multiple relations between the edges sometimes. We have a heterogeneous graph, and we need to cater for that in our update function, okay? So all we do is, instead of taking a sum of all of our neighbors, we need to differentiate between all of the different relations, okay? So here I'm having, for each relation, I'm looking at all of my neighbors that fit that relation. So all of my left neighbors, I aggregate them, so I transform them with a linear transformation. I aggregate them together, and then all of my relations just help me update my representation, okay? That's how it works, round about, okay? So here we have, again, the neighbors are going to normalize the constant, so we're basically taking an average, and then we're using an activation function to have an updated node representation, okay? And we do that for all of the nodes, which allows us basically to learn a representation of our state space, okay? So this is really good because now what we've basically done is we have a structured observation that we can learn over, that we can feed into our reinforcement learning architecture, no matter what it is. I'm not going to talk about this because this could be another half an hour. The point is we could feed that into any reinforcement learning method, okay? It's just about learning the structured observation, okay, that now informs our value function, our optimal behavior, okay? So basically what we can do is an end-to-end transformation where we can then learn, based on the values of our states, how we want to represent this in the graph neural network, okay? And yeah, there's a bit of information in the case of multi-agent reinforcement learning. We can share this component actually amongst agents, because at the end it's a spatial encoder. You could see it as a spatial encoder. And even if you had individual rewards or if you had a competitive behavior, learning the spatial understanding is the same for everyone. So you can share the parameters, which is much more efficient, okay, compared to other methods. And then we can learn this all in a centralized way, which basically means during training, we can just share all of that information across the agents, which is another detail that I probably wouldn't get into. And yeah, that's basically the idea, okay? And that we tested on the environments that I've shown you, okay? And for the first step, the in-distribution performance. So here what we see is actually, so these are examples. So the level-based foraging was the one with the apples and the fruit, the apples and the agents on a 10 by 10 grids with 4 agents and 4 fruits, and you need to cooperate in order to pick up the fruits. And what we see here is actually the most difficult setting because you have a lot of entities. You have to cooperate, and the fruits stay on the grid. So you need to understand what are fruits that you already picked up and which ones you need to pick up still. So it's a really difficult setting for our little agents, okay? And what we can actually see that first off, we learn things really quickly, as you can see in all other settings. but we're also asymptotically really good, okay? Because this is an example which is really relationally complex because of the things I've mentioned, okay? So we're actually really picking up a good job in actually learning over the structure. Forcing the structure helps us to be sample efficient and actually learn what we need to do, okay? Whereas with the other cases, which are easier, but maybe here we have a much more scaled version where we have 8 agents, and you can see actually that we're much quicker in understanding what we need to do, okay? The second thing was the generalization performance, okay? And here it was, again, we're trying to train on one setting, and then we tweak little bits in the evaluation, okay? So what we want to treat here is, in the case where we have 4, like we tested on 4 agents and 4 fruits, we want to vary the number of agents and we want to vary the number of fruits, okay, and see what happens. And here it needs to be said that actually a lot of methods cannot cater for that at all, because what you feed in is a fixed vector or fixed grid, okay? So if you feed in a fixed vector, you can't actually change the number of entities because that changes the size of the vector, okay? So a lot of these methods are not even applicable to the generalization setting, okay? So you can't even test that on that, okay? So what we've done here is we've taken the second, like the best performing baseline, MAPO, and trained it on these settings, okay, to compare to. So whilst our method is evaluated, trained on 4 agents and 4 fruits, and then tested on these settings, where we reduce the number of agents, this method is actually trained on this setting, okay? Which is obviously much easier because there's just in distribution samples that it's trained on. However, we do manage to outperform it for quite a few cases. So this is, for example, here, if you reduce the number of agents, that is the difficult setting, right? Because the less agents you have, the less time you have to pick up all of the fruits and stuff like that. So this method actually didn't really do well on that case anyways, and it really fails if you reduce the number of agents, okay? Whilst we actually 40% is not bad. It's not amazing, you know, but it's actually quite robust compared to what other methods can achieve. Same with the number of objects of fruits, okay? So the more fruits you have in an environment, the more difficult it is to get all of the rewards, right? Because the harder it is actually to collect all of them. And we're actually managing to still actually achieve quite good results, depending on even with six fruits, okay? Whereas the MAPO, which is the baseline, actually only gets 20%, so less than a third, or around a third, okay? So that's really promising result, and I think we can actually, we can still very much push that a bit, but it's a really strong indicator that how when we use a graph in order to represent our state space, we're much more flexible on what we want to represent, and we learn a much more robust policy here, okay? Little bit of ablation, and I'm not going to go into detail too much about it. In terms of how we construct the graph, which is the main message, how you construct the graph is actually very, very important, okay? So the number of relations I've shown you, 6 relations. If you increase that number, yes, sure, it would work, but your computational time would increase by quite a lot, okay? Similarly, if you use different aggregation methods, so whoever heard of transformers, you know, the things that are so famously now in LLMs, if you use a more attention mechanism to actually learn the importance between your nodes, actually that's not a strong enough bias that we would have here, because the spatial bias we introduce is actually quite strong, and it helps us learn the sample efficiency that actually attention cannot. Other than that, also the number of entities makes quite a big difference, okay? So if you were to take the whole grid, because you wouldn't know what an entity is or not, you would first off, you would learn something, but it would be much slower. And in this case, computationally time actually, it costs you quite a lot, okay, because they're really computationally intensive methods here. So yeah, that's just to give you a gist of that. In terms of future work, I mean, there's so many different possible ways, but what I really find interesting is there's so many more graph neural networks and ways you can, graph neural networks are so flexible, okay? You can decide on how you design your graph, what information you want, what relations you have. We only work with spatial relations because they're so convenient, because they're always there. But you could add you can add semantic relations, okay? You can add a lot of things into your network depending on the information you have. Another thing is actually there's work coming out that actually works on graphs itself. So graph environments that are not on grids, but on graphs, okay? It's a really interesting area. And also to make it more explainable, because we have structure and we see that we learn a robust policy. So actually understanding or making explainable what our model learns is quite interesting in our case, because we do learn a structure. And on the model-based side, yeah, basically said like you can push the generalization much more and actually kind of add much more generalization capabilities or transfer it to even slightly different tasks and see if it performs well. And a really interesting case is also safety in RL, because if you want to talk about safety constraints and reinforcement learning, it's a really good thing to have structure, because that's basically what you need. Okay, you want to enforce a structure so you know that your model is learning something in a safe way. Okay, so applying these kind of methods to there, I think, could be really interesting and would hold a lot of promise. And with that, I'm done. Thank you very much.